This is chapter 28 lecture. It's part 3. It's probably going to end up being 4 parts. This, like I said, is a long chapter, has lots of detail. And, you know, I want you to get more in-depth information on microfabrication, since that's something you won't be seeing much of in other classes unless you take Dr. Jackson and my senior level classes on MEMS, microsystems, and nano. Okay. All right, so the picture you see there is a deprocessed computer chip. What's left are the metal contacts. So you can, the reason I like to show this this image to everybody is because it shows the detail and the intricacies of making a computer chip. So you can see there are multiple layers of metal that connect different components to each other. So as we mentioned earlier, you have to take your design that you do in CAD. There's different kinds of CAD programs that are used for designing microelectronics and micro transducers and actuators and sensors. So you design this in layers, and then you transfer the layers onto the wafer surface, and you pattern the different materials that you use in building this product. So it's a layer by layer process. So at each layer you have to do what's called photolithography. Okay, and that's what this slide shows you. It's a basic process set of steps. So you start with the substrate at top. That's usually a crystalline silicon wafer. You apply some photoresist on top of the substrate. So in this case, the substrate could also be a layer on top of the crystalline silicon. So this is repeated step after step after step. Okay, the photoresist is a coating that you use that's sensitive to light. Okay, and that way you can transfer a pattern from the mask, that's step 2 here, onto the photoresist. So the mask is showing in a side view, and it sits above what you're trying to transfer the pattern to. And the mask is made up of, basically it's chrome. Generally it's chrome on glass, and the glass is typically material that is transparent to the light you're using. So in the case of I line and G line, you know, near ultraviolet wavelengths of light, the chrome usually is patterned on top of a quartz piece of glass, because quartz is clear to ultraviolet light. So you shine some light through the mask, and it exposes the photoresist where it's allowed to go through, and it doesn't expose the photoresist in areas where it's not allowed to go through. Okay, so now you have a region where the photoresist has been exposed to light and where it hasn't. And in the case of positive photoresist, which is what most people use, and that's shown on the left side at the bottom of the graphic, whatever is exposed ends up being developed away. So in the case of positive photoresist, you expose the photoresist with light. The photoresist captures the ultraviolet photon, and that's through a photoactive compound, and a chemical reaction occurs which causes that part of the photoresist to become slightly acidic. Okay, because it's slightly acidic, it can be developed out with a basic solution, which we call developer. Okay, so this series of steps is pretty typical for transferring your design onto the wafer. Do you use a different mask for positive and negative photoresist? Yeah, it depends what you want to have remain on the wafer. So you might have the opposite image on your photo mask. So on the left side, it's the positive photoresist, which we like to say what shows goes. So whatever's clear is what gets developed out. and whatever isn't won't get developed out. So you can see the photoresist remaining on the surface is protecting what's underneath in for the subsequent etches, and that'll become more apparent as we go through the process steps. So with contact printing, the photomask is basically in contact with the photoresist, and that's shown here. Okay, so you can usually transfer patterns that are as small as 1 to 2 microns routinely using contact printing. It's a cheaper process. These machines are on the order of $300,000 to $500,000 each instead of $3 to $5 million each. Okay, so they use contact printing a lot in MEMS because most of the small structures are on the order of 1 or 2 microns or greater. You can do direct write with electrons. So you can have an electron beam actually write out the pattern on the wafer, right? But it's extremely slow. You can imagine trying to move that electron beam across the wafer to transfer your pattern onto the wafer. And the electron beam is controlled by a machine that reads your design off of a CAD drawing. Okay, but you can go to extremely small geometries with that, on the order of 1/10 of a micron. So actually electron beam lithography is used to making the photomasks, because with photomasks you can take a long time to make one mask, and then you repeat, when you make your computer chips or your MEMS devices, you use the mask over and over and over and over again, and it's a very quick process at that point. So electron beam lithography in industry is only used to making the masks, and in research they use it occasionally because they can make very fine structures for prototyping and testing circuit ideas and circuit designs. Then they don't have to make a full-blown mask and use a $400 to $100 million photolithography machine, so the cost benefit's better for doing research. It's kind of like using a 3D printer or doing something in mass production. And we can also use X-rays. X-rays can go to very small structures. They use proximity masks for that. Typically, X-rays use gold on beryllium substrates as the mask material. Beryllium is clear to X-rays. Okay, if you used chrome on quartz, it wouldn't work. So gold stops X-rays really well, and beryllium is transparent to X-rays. And it's the same sort of process, but you use a different kind of light. You can do direct writing with ion beams. So ion beams can actually ablate material off of the surface, and you can either ablate the photoresist or actually do ion beam milling of the material itself. And again, since that's a beam, it's difficult to do in mass production. You can have broad beams of ions to do a larger area, but again, it takes a lot more time to make one wafer or transfer one pattern. So time is money, right? So here's a little detail on how you coat the wafer. So you apply some photoresist onto the wafer. Okay, so you have a vacuum chuck. So the chuck itself is under a slight vacuum, so it causes the wafer to stick to the chuck. You have to make sure the wafer is centered. And in high volume production, they use robotic systems to do that, and it works really quickly. In small production and startup companies, they will place the wafers by hand onto the chuck. And that's what you would have done had we had the lab this semester in the clean room. So we dispense some photoresist onto the substrate, and then we spin it. Okay, and as it spins, the photoresist is spread across the wafer, and hopefully uniformly. Okay. And then once that's done, we stop the spinning, we take the wafer off, and we do some evaporation on it. So we put it on a soft bake plate to evaporate the solvent off. Okay. And of course, the devil's in the details. If you don't have a good spin program, if you ramp up too fast or too slow, you'll get non-uniformities in the coat across the wafer, and that's important in terms of the quality of the transfer of the pattern to the photoresist. So when I was in industry, I worked closely with coat engineers. I was a photolithography engineer, and then we specialized in certain tool sets. So, my buddy Dave would do tons of tests on spin speed and exhaust flows and all of that to try to get the perfect coat. And you also want to use as little material as possible because photoresist is very, very expensive. So you can get away with a lot of problems by just putting a lot of photoresist on the wafer and then spinning it. It becomes very uniform. But as you reduce the initial volume, it becomes more and more non-uniform when you're done. So our goal, of course, was to save money. So we had a big project at TI to reduce the amount of photoresist dispensed on the wafers. And we actually went from 2 milliliters down to 0.8 milliliters, which was a huge savings. I think it was on the order of $2 million a year in photoresist, just for one type of photoresist that we were using. So that's an example of some of the work you do as an engineer, as a process engineer, working for a place like Texas Instruments or IM Flash. Okay, so once you put this photosensitive material on top of the material that you want to transfer a pattern to, you expose it. And we went through some of the other exposure methods with the ion beam and the electron beam X-rays. Those are more esoteric. What's commonly used in industry for the most part is what's called an exposure stepper. Okay, and here you can see the cartoon. It schematically shows you have a mask that sits above a lens. Okay, and that lens demagnifies or shrinks down that image on the photomask onto the wafer. And you do one region of the wafer at a time. So it's called a stepper. So it steps across the wafer. So it'll generally start at either the top or the bottom of the wafer and expose each of these regions one step at a time as the wafer moves underneath the lens. Okay. So that's the basic idea. And they call this mask up here a reticle. So typically, if it's a contact printing system, a one-to-one with no lens in between the mask and the wafer, that's called contact printing, and it's called a mask. If you have a mask that you're going to use in a stepper, they call it a reticle. And it has to do with because you're changing the magnification of the pattern. That's why they call it a reticle. So it was very interesting when I was at TI, they called it reticles. And when I went to work for Philips Semiconductors, they switched terminology and they called it masks because they started with masks in the old days. So they kept that term. And then in order to get even better resolution and depth of focus and all that, they actually expose only a little part of the mask and the wafer at a time. And they have a slit that's open that goes across the mask as they move the wafer underneath. And that's called a step and scan system. And the reason you can do that is if you're only illuminating a small slit on your lens, you can find the best part of the lens to use. And then you reduce lens distortion. So the lens stays still and the mask and the wafer move, generally in opposite directions because the image is usually flipped, right? So they go in opposite direction. And as you expose, you can also move the wafer up and down to keep it in focus. And you can move it, you can tilt it as well. So since you're only exposing a small region of the mask at a time, you can keep that region in better focus throughout the process of transferring that mask pattern onto the wafer. And it's called a step and scan. So that was another evolution in the stepper designs over the years. So I was in industry when they started bringing in step and scan tools, and they were another order of magnitude more expensive than just the steppers alone. But to give you an example of as to why industry switched to step and scans, one was they can make smaller stuff. All right, you make smaller stuff, you get faster computer chips, and you can put more chips in a square inch on the wafer. So you get a cost benefit there, even though the machine's very, very expensive. Okay, so that's one reason. But the step and scan tools, they actually improved them so much that they could produce 3 times as many wafers per hour. So now instead of having 3 steppers, you could have 1 step and scan tool. And they did innovative things like have 2 granite stages. So on one stage, they would pre-align the wafer while the other one's stepping. And then they'd switch the 2 stages and then continue stepping. So there was no pause or very little pause between wafers. So they could crank these things out very quickly. Okay. They also went to chemically amplified resists, which means that they were faster because it takes a certain amount of time to expose photoresist. But if you create faster photoresist, then you need less light. So that means each step takes less time. Okay. So there's a lot involved in these things. All right. I love this cartoon. Everybody knows or has heard of Moore's Law. Okay. And this is a graphic showing what that means. Okay. So let's take a look at this. If you want to give it a shot in the chat box, the question is, what was the minimum feature size in 2010? In 2010. So try to figure out, how to read this graphic and see if anybody can come up with that. See if I can do it. C, 40 nanometers. B, 40 microns. Well, take a look at the axis. Okay, it's in nanometers. All right, so it would be C, right? You come across, I hope you can see my cursor here. You come up from 2010, look at where the line crosses. This green line, right, is pointing to the left. So you use the left axes. Okay, the red line actually points to the right, so you use the right axis. So you can see as we make things smaller, right, we can put more transistors per chip. Okay, so in the old days, we had about 10 kilobytes, right, 4,000 transistors on a chip. And that was the Intel 8080 chip back in before the 80s, right, and probably mid 70s or so. And you can see every few years things double, right? You get twice as many chips. I think it's doubling every 18 months is what Moore's Law is. So as you go up, right, you can see we're getting more and more transistors per chip. And you have to remember, this is a log graph. So if I go from here to here, right, I'm going from 20, okay, up to 40, okay, on the minimum feature size. We actually have to look at the right graph. So this is again in a log. So we go from 10 to the 4th to 10 to the 5th. So how much time did that take? If we go over here, we're about the mid 70s at 10 to the 4th. And then we go 10 times more by 1980. So in 5 years, we went a factor of 10 in the number of transistors per chip. Okay, and then we dropped in the same amount of time in the minimum feature size. Okay. We dropped quite a bit, 1/10 the size or so. So remember, if I make something half as big, right, in X and half as big in Y, I can put 4 times as many in the same area. So shrinking something in half allows you to have four times the transistors. Okay, so that's what was driving this. And you can see, you know, we get up to the Pentium 4. That's when I stopped keeping track of all of these things. But in 2010, we were up to 10 to the 10th transistors per chip. It's kind of interesting. They put the number of neurons in the human brain up here. But you have to remember, it's a little different. You can't compare the brain with a computer chip in terms of computing power, because transistors only have one input and one output. Neurons have multiple inputs, multiple outputs, right? And also they have an intensity output. It's not just 0 or 1. So the neuron can fire a little stronger signal or a little weaker signal, and then different things happen in the brain. So if you want to compare computing power, the brain's still way off the scale here on this chart. So we've got a couple of questions. A very good one: when will the number of transistor ever peak? So they're reaching limits to how small they can make something, right? So that's kind of one limit. So Moore's law, you know, they always say is going to end someday when you get small enough, but they get also more complex. So they're learning how to stack transistors. So instead of just having one transistor in a certain point, they can have multiple transistors in that area. So the ion flash people that do those terabyte memory chips and things like that, they'll have 2 layers of transistors, and they're working on 3 layers of transistors. So yeah, you're not getting any smaller in the XY direction anymore, but you're learning how to make them and make them go up. So it's kind of like a skyscraper, right? So of course it's very difficult to do this. And then you also have to ask, well, why do you need it so small? You'll get to a certain point where, you know, smallness doesn't matter anymore, right? Your phone can have enough computing power in it with the high-end chips that we have now. Do we need to go more? Maybe on the digital processing side, if you're streaming video and that kind of thing. You know, it's always the video card drivers that drive this industry a lot. The gaming guys started it with the PCs. So another question: when quantum tunneling becomes a problem because it's too small? Exactly. If you have two, we even saw it in my day, when you have 2 wires really close to each other, right? And you have a signal going down one wire, the other, it acts as an antenna, and the other one acts as a receiver. So you can actually have signals jump from one wire to another if they're too close together and there's too much current flowing. So when you're talking about tunneling, you might have an electron. If you're down to very small signals of a few electrons rather than thousands of electrons, there's a probability that that electron can jump from one place to another through quantum effects. And that probability gets higher as you get closer and closer and closer together. And you can also get tunneling through the p-n junction, right? If the channel on the gate gets too small, you can have the electron jump across. So quantum computing actually leverages that, but then you have to design the circuits in a way that you can take advantage of the quantum computing. So since there's a probability your 0 can flip to a 1, then you need several quantum systems. And that way you take a vote, right? Is it a 1? Is it a 0? And then you just take a vote. So it's kind of an interesting thing. It's beyond what I know, but I know there's some people at UNM in the physics department and in computer science that are working on quantum computing systems. Yeah, so once they reach a minimum, they'll start becoming bigger, but they'll become bigger in the Z direction. So right now the chips are extremely thin. You know, you can put an entire computer chip in maybe 10 microns in height, or maybe 20 microns in height, right? Which is 1/5 of the human hair, and your phones are very thin. So circuit boards tend to be very flat, right? And with very thin chips on them, even with the packaging. But now we're learning also how to stack chips. So we'll make one chip, we'll make another chip, and instead of putting them next to each other, right, we put them on top of each other and connect them that way. So now you make that area smaller, right? Instead of having this much on your circuit board, you have this. And then you can stack more chips on top of each other. It gets a little bit of a problem with thermal issues, right? Because whenever you move current through a wire, you produce heat. So you want to keep the resistivity down to produce less heat. You want to keep the voltage down, right? Because power is I squared R, or IV, current times voltage. So if you keep the currents low and the voltage is low, you can reduce the amount of heat produced in the chip. Okay, in the old days, you might, if you were a gamer, you would see the CPU chip on the circuit board, and then they would put this thing on it with fins to suck the heat out of it, right? So your chip doesn't overheat. Okay. And people have played with microfluidic cooling too. So you actually put cooling channels like a radiator in a car, right? And you run fluid through it, because fluid does a better job at pulling heat out of things than air. So people have done that as well. They've also mounted fans, right? Muffin fans, and they'll even put a fan right on top of the CPU on the older designs. But we used to be at 5 volts, and then we went down to 3 volts. I think the transistors are running around 3 volts now. So reducing the voltage has helped a lot with the heat issues. Okay. All right, so like we said, the first step is creating a pattern, right, in the design side, and then that pattern is put onto a mask, and then the mask is sent to the factory where you make the chips. Okay, and then you transfer the pattern onto the wafer. So here we show how that works and then what happens in the next step. So here we start with a very simple material called silicon dioxide, SiO2, that's on the left side. Put your photoresist on it, okay? And then you transfer a pattern into the photoresist, and that's what that dash box is showing. Okay, so they show the negative and the positive version of it. Like I said, we typically use positive photoresist for most things. And then, you know, wherever the photoresist has been exposed, if you're using positive photoresist, gets developed, and that's what they're showing in step 4. Okay, so wherever the light is hit, right, this is the clear area on the mask, this is the chrome. So the light goes through the clear part, exposes the photoresist. That looks like the darker gray when it's been exposed, and you can actually see an imprint after expose. Okay, so you know, now you have a region that has been exposed and a region that hasn't. Then you go ahead and develop it, and that's usually done in a base solution. So now you've developed that pattern. So you can notice that silicon dioxide is now exposed, right? It's exposed to the elements, as it were. So then we can do some etching. And you can etch silicon dioxide in a multitude of ways. There's dry etching, where you use a plasma etch, kind of like a blowtorch. Okay, it's a little more controlled than that. Or you can use wet etch processing. Okay. So the wet processing can also remove whatever's exposed. So the photoresist acts as a blanket or a protection layer from the elements. And then wherever it's open, you can etch away. Okay, and then once you've transferred that pattern from the photoresist into the system below, Once you've transferred that pattern, you don't need the photoresist anymore. So you remove it. So in a nutshell is you have a mask, you put photoresist on top of the material, you transfer the pattern of the mask to the photoresist, you develop the photoresist, and then whatever is exposed is going to get etched away, and then you etch what's exposed, and then you take the photoresist off. Okay, so it's a pretty straightforward process. And again, if you're an engineer working at a TI or an Intel or Philips or Global Foundries or IM Flash, any one of those places, it's the details that you have to learn to control. So you have lots of process control charts, you have to verify the quality of the materials coming in, and all of that. So you do a lot of measurements all through the process, and you monitor those measured outputs, right? And then you respond to that when they go out of control. Okay, positive and negative photoresist, as we said, we just reverse the image. Okay, so what we say with positive photoresist is what shows goes. So that's an easy way to try to remember it. So we can also transfer patterns into photoresist without using light. We can use molds. Okay, so you can make a mold and then transfer a pattern. So the previous slide showed a pattern photoresist that's going to act as a mold, and then they use PDMS. They coat the wafer with PDMS, and then they take the PDMS off, and they have a cured PDMS stamp. And these stamps are used to push in a pattern into a softer material. So they often do that to transfer microfluidic channels and things like that into a substrate, into a material to use as microfluidic channels for chem labs on a chip and things like that. So kind of like the COVID-19 antibody detection system has some microfluidic channels in it, and some small heaters and things like that. And it's about the size of a, I don't know, USB thing. Okay, so PDMS stands for polydimethyl silosane. Okay, so but it's a mold for soft lithography. Okay, so this is how you would go ahead and transfer patterns into other materials and making stamps. And again, these are on a very small scale. So we're talking about making small things. Okay. And then this shows you can make all sorts of different structures depending how you process it. So here we have a bunch of little channels. We put liquid polymer in there. It actually flows inside the stamp, and then you cure it. Okay. So that's a way of transferring patterns onto the system. How do we get the materials on the wafer that we're going to pattern? Well, one way is called CVD, and that stands for chemical vapor deposition. Okay, and we mix chemicals in a vapor form. We usually heat it up, so we get a chemical reaction, and we create the material that we want, and that material forms on the surface of the wafer. Okay. So here's one way to do it. They actually have a conveyor belt. This is old school, and they're starting to use this a lot with like flat panel displays because they can do large area things with it. So this is an APCVD, which is atmospheric pressure chemical vapor deposition. So it's not in a vacuum or low pressure. It's at atmospheric pressure. And if you look at the left and right side of the system, they're actually pumping nitrogen gas in, and it acts as a curtain, right? A nitrogen curtain, so the atmosphere from the outside doesn't get inside the chamber. And the wafer goes underneath the curtain, goes through the curtain, right? Like you're walking through a gas curtain. And goes into the machine. Then you flow whatever gases that you have of interest that you're going to make whatever material you're going to make. Okay, And you have a heating system because chemistry works better at temperature. Bonds can break and reform and that sort of thing. So you flow your wafers through on the conveyor belt, and then when it comes out the other end, a robot picks it up, puts it in a carrier, a wafer carrier. Okay, so this is a schematic of it. Here's another one. This is a low pressure chemical vapor deposition. So this is done under low pressure. Okay, so you pump most of the air out of the system and then you flow some gases in. So this is what I'm more familiar with. This is what we had at TI and at Philips Semiconductors. So this is a horizontal, we called it diffusion furnace, chemical vapor deposition tube. You know, there's lots of different terms you use. But it's essentially an oven, right? And it's in a cylindrical form. So you're looking at a cross section. On the top and the bottom are the heater elements, right? Usually you just pour a lot of current through wires, and the wires get hot, and you can make it, you can raise the temperature inside that furnace. And we typically go up to 1,200 degrees Celsius. So that's pretty hot. All of the materials used to put the wafers in and take them out, and the tube that they go into, are made out of quartz. So quartz doesn't melt until it hits about 1,400, I think, degrees Celsius. Okay, so we don't want to go higher than that because then everything melts. But we can maintain this temperature for very uniformly for a long time. And so the way it's done uniformly is you have different zones. In this case, it's a 3-zone furnace. So you control the current going through the wires in each zone, and then you have thermocouples monitoring the temperature. So the current is adjusted to maintain constant temperature throughout the entire tube. Okay, and then the wafers usually are stood up with some space in between them. And that way, when you pump in your gas, chemical reaction occurs and puts a material down. So a common material that we use is polycrystalline silicon. That's why we learned about polycrystalline structures, right? And the way we deposit polycrystalline silicon is we need a source of silicon, and that's silane gas typically. So we'll flow silane gas in there, and it breaks apart in the heat, right? And the silicon actually forms on the wafer in small crystals, polycrystalline structures, and we can grow or deposit. Actually, we deposit the polycrystalline silicon on top. And we can also put silicon nitride down, and that's a combination of dichlorosilane and ammonia gases, right? The ammonia brings in the nitrogen, the silane or dichlorosilane brings in the silicon. The silicon and nitrogen break apart from their carrier gases and then recombine and create silicon nitride. Okay, so you can make a couple of different, or quite a few different materials. Typically you make oxides and then poly type materials, silicon-based materials, when you're making semiconductors. Okay. So we can also grow silicon dioxide if you put a bare silicon wafer in the furnace and just heat it up and put a little bit of oxygen in there, or a source of oxygen. The oxygen will combine with the silicon, right? So that combination of silicon and oxygen ends up creating silicon dioxide. Well, if you remember in old school, maybe in middle school, you learned about how things rust. FeO2, right? Ferrous oxide is rust. It's the same thing. You're combining oxygen with iron and you get rust. You combine oxygen with silicon, you get silicon rust. Okay, so, and we use silicon dioxide as an insulator, okay, oftentimes, or as a sacrificial layer between moving parts, if you're making MEMS devices, and then you remove the silicon dioxide when you're done. So to give you an analogy with 3D printing, right, if you're going to make 3D printed parts, sometimes you need a sacrificial material in between to hold up the two two different layers that you're making, and then later on you remove what's in between, and then the parts can move relative to each other. Okay, so some of you may be familiar with that. Okay, so we can make silicon dioxide by using heat, oxygen, and a silicon source, which is the silicon wafers. Okay, and again, we do this at a high temperature. Silicon wafers will rust in the, just sitting around, but they stop forming an oxide layer after 1 or 2 or 3 nanometers in thickness of oxide. And the reason is the oxygen can no longer get through the formed oxide layer to interact with the silicon substrate. So that's called native oxide. And sometimes we strip that off and then put another material on top to get rid of that very thin oxide layer. Okay. And even if you leave it out for 10,000 years, it won't get any thicker. Okay. That's why we have to put it in a furnace at really high temperature. Then those oxygen molecules are moving really fast, and they can get through the oxide that you've already created and be able to react with the silicon that's underneath the formed oxide layer. Okay, here's a video on etching basics. I'm going to skip this. You guys can click on it with the lecture slides. I'll probably post it as a separate video. And if I have time, I'll try to insert it into the lecture at this point after the fact as well. Okay, but I recommend that you watch this video after, thinking about what we've already covered and reading the book, and then it'll make a lot more sense to you. Okay. All right. So we can do different kinds of etches, right? So a mask material, that's the material protecting what's underneath, can be photoresist, like we talked about, but it could also be a patterned layer like a silicon dioxide layer or silicon nitride layer. Okay, and then you have openings. Now, let's assume we're going to try to etch some silicon, the silicon wafer itself. And here is a pattern, say, silicon nitride. So we have an opening here that can allow chemicals to come in, plasmas to come in, and start etching what's underneath. So this is called isotropic etching. So you need to know this. You need to be able to identify this picture with the type of etching it is. So iso, you might want to write this down. Iso means the same, right? Like an isosceles triangle, the same. The two sides are the same, right? So iso means the same. Tropic means direction. So if you have an anisotropic etch, that means you're etching the same in all directions. Okay, so what you're seeing is we're etching down as we are etching across. And you end up forming something that looks like a bowl. So that's an isotropic etch, same in all directions. This is an anisotropic etch. And means not. Okay, and iso, same, so not the same. By the way, tropic is like a direction. So it's, if you remember from geography, there was the Tropic of Cancer on your globe. Well, that's a direction. Okay, so anisotropic means not, and means not, same direction. So it doesn't etch the same in all directions. And this is an example of an anisotropic etch. So here we're etching crystalline silicon with something called potassium hydroxide. Potassium hydroxide will etch one plane a lot faster than another plane. So the plane on the surface of the wafer, and we talked a little bit about that, in this case is the 100 plane. The 100 plane etches at about 1.2 microns per minute, okay, at 80 degrees C for potassium hydroxide at about 30% concentration, okay? So it's etching down, 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 but it etches the 111 plane more than 1/400th slower. So effectively, it doesn't etch the 111 plane. So it follows the 111 plane down. Okay, and you can see it following down. And if we let it keep etching and keep etching and keep etching, the planes will finally meet, and for all intents and purposes, the etch is stopped. So you can make a nice V groove that's very well defined. The depth is defined by how much your opening is on top. So you can leverage that crystal structure to get the different shapes. And you do that through anisotropic etching. Okay, in this example, the material here, the hard mask, is most likely silicon nitride because that doesn't etch in potassium hydroxide. Okay, so you got to pick a mask material that stands up to the etch that you want to do. And the etch is determined by what material you're trying to etch. So there's a whole range of chemicals and plasma etches you can use to make different structures. So take a look at this, right? And if you want to give it a shot, is this anisotropic or isotropic? Remember the definitions of iso and aniso. All right, so those of you who answered got it right. It is anisotropic. It's not the same in all directions. Okay, so you can also etch very straight walls down. And there's a lot of different ways to do that. Okay. So now we're going to talk about selectivity. So selectivity is something engineers have to be concerned about because whatever you're protecting during your etch has to stay around long enough to continue protecting your etch. Think about it a little bit. So it's the relative etch rates of two materials. Okay, so here's a typical question, right? If my photoresist etches at 10 angstroms per second, and the material, say silicon dioxide that's underneath it, etches at 100 angstroms per second, what's the relative etch rate? Okay, so the way you do that is you say, okay, how fast am I etching the material I want to etch compared to the material I don't want to etch? So it's 100 to 10, right? So I'm doing 100 angstroms of silicon dioxide for every 10 angstroms of resist. I don't want to etch the resist. I want it to hang around as much as possible. So it's a 10-to-1 ratio. Okay, so most of you got it right. And you know, what do you want? Typically, you want a higher selectivity, right? That's what that means. So it's the higher selectivity that's important. And you'll have some homework questions around that. And then here's a nice little table from the book. Okay, it's showing you etching of silicon crystal as a function of different planes. Okay, sometimes it doesn't make a difference. Sometimes it makes a lot of difference. So you can see in the second row there, it says KOH. K is potassium. OH is hydroxide. So potassium hydroxide will etch, you know, anywhere from half a micron per minute to 2 microns per minute, you know, with that temperature range. And the selectivity here is 100-to-1. Okay. So I think it's actually a little higher than that, but it doesn't etch the 111 as fast as it etches the 100 plane. Okay, and then if you use nitride, nitride is short for silicon nitride. You can see that doesn't etch at all in potassium hydroxide. So that makes it a good mask material, right? That silicon nitride isn't going to let anything through it, at least potassium hydroxide. Okay, now if you were to use silicon dioxide as your hard mask material, because you could do that, it's going to etch at 10 nanometers per minute. So you better have a thick enough silicon oxide layer on top of your silicon in order not to break through that silicon dioxide and start etching the silicon substrate in this case. Okay, so that's real important to know. We did some work one time and we thought we were using silicon nitride deposited wafers because they look a lot like silicon dioxide. deposited wafers. So when we did our etching in the potassium hydroxide, after about an hour and a half, we lost the wafer. The wafer dissolved completely in the potassium hydroxide bath, which was kind of funny. So we put 6 wafers in and we ended up with 4 because 2 of them had the silicon dioxide as the masking material instead of silicon nitride. So you got to pay attention to what your wafers are. And then here are some other examples. Down at the bottom, you can do dry plasma etching, right? So SF6 is what you use to etch, or you can use a combination of SF6 and C4F8. That's called deep reactive ion etching. So if you take our upper level classes, we'll go into more detail on that. And then this shows you how to etch other materials. You know, you can etch metals, you can etch oxides, nitrides, all of that. And you use different etchants and different methods. So you can use a wet etch, which is chemistry, which is in a bucket, right? Or you can use dry etchants, which is in a plasma chamber. Okay. So we do both of that in our clean room. So if you ever have an opportunity to do research or take some of the classes we have in our MTTC clean room, you'll get to play with that. And this shows you relative etch rates. I think there's a homework problem on this, asking you to be able to read this type of a graphic. So again, a rate is distance over time, right? It's like a velocity. So how many millimeters per hour am I etching? Right, so you can see the 111 plane etches a lot slower than the 100 plane or the 110 plane. Okay. And it's also a function of temperature. So the higher the temperature, the faster you're going to etch. Okay. And you're already answering the questions. How much faster does 100 plane etch relative to the 111 plane? So you can see the distance is relatively the same. You can just look at one line. Here I'm going from about 10 to the 0, you know, all the way to 10 to the 1. This would be 2. Let's see, 1, 2, 3, 4, 5. So this would be 10 millimeters per hour. I think this is 40. This would be 60. Not quite, but you get the idea. You have to kind of look at it, and it's roughly, this would be 10 times. It's almost 1,000 times or 100 times, right? 100 times faster. Okay, so here we're doing it in EDP instead of potassium hydroxide. EDP is a etchant used to etch crystalline silicon that's compatible with making computer chips. So they'll use this material when making things such as inertial sensors, micro inertial sensors, where they have to etch out some silicon and protect the computer chips, you know, the logic part of the chip. And they can do both processes together using EDP. The only downside to EDP, it's cancerous as heck. So you don't want to get it on you. So most industries will avoid those kind of things because people work around these chemicals, you know, often, right? All day, every day, you know, 2,000 hours a year, you know, that kind of thing. So long-term exposure becomes important. It's not like you're just doing something real fast in your garage once every 10 years. You're using it all the time. So you got to be aware of the safety aspects of the chemicals you use. They may be great chemicals to do processing, but you got to look at the effect on your employees, right? So if you design a process, make sure it's safe for your employees, your coworkers, and also what do you do with it when you use it up? You can't pour it in the river. right? So how do you dispose of it? So those are cost analyses you do as an engineer as well. So you want to keep people safe. So if there's a safer alternative, great. If it's better for the environment, that's great too. And if it's easier to dispose of, that's great. And then if it's cheaper, it's even better, right? But sometimes you don't get to hit the trifecta there. All right, let's continue on. So let's see, it's 10:34, so we've got about 12 minutes left. Let's combine everything that we've just learned. So photolithography and etching of silicon and depositing of silicon nitride. We've learned a lot, right? You probably want to review this stuff and read more about it, but we covered all of that material. How do we make a membrane? So let's say I'm a mechanical engineer and I want to make something that flexes. Okay, maybe I'm going to make a pump, right? Diaphragm pump. Maybe I want to measure pressure difference, so I'm going to look at how much my membrane deflects and have two different pressures on top and the bottom, right? The pressure difference between the top and the bottom of the membrane. And I want to take that membrane and it's going to deflect, and I can measure how much it deflects by and then get an idea of what that pressure change is. So I'm making a sensor in that case. So I can make a sensor with a membrane, or I can make a pump, right? An actuator. I can do something to the world. So how do you make a membrane using an etch stop? Well, this is really interesting. If you dope the silicon, right, the potassium hydroxide won't etch the dope parts of the silicon. So you put a little bit of a dopant on top and on the bottom of the wafer, and you drive it in. You can do that through implant, right? An ion implant machine, which is typically what they do in industry. Or you can put what's called a spin-on dopant and then put it in a furnace and anneal it, right? And then it'll diffuse. So when you learn about diffusion and fluidics and that kind of thing, your upper classes, you'll get the idea. So you can put a material in, heat it up, and it'll diffuse into the crystal. And as a result of that dopant, you can stop etches right away. It changes the surface chemistry once the etching gets to that point, and the reaction cannot occur anymore. So that's called an etch stop. Okay, so here we see we've taken some silicon dioxide, we coated both sides of the wafers, we went ahead and we did some patterning, so we have some silicon dioxide left at the top. Now we do some doping. Okay, so we dope the regions. So where the silicon dioxide was, we didn't dope that silicon. Okay, and then we diffuse it in with a diffusion furnace. Okay, and now we start etching from the back. So if you look at the previous picture, we also patterned the back of the wafer. So this part of the silicon crystal is open. It hasn't been doped. So when we expose the silicon to the potassium hydroxide, it's going to go ahead and etch all the way through. Okay, and it follows the 111 plane, right? The potassium hydroxide. And it keeps etching, 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 and then it gets to the boron doped region and stops etching. But then this region isn't doped, so it keeps etching through the silicon till it hits the silicon dioxide on the other side. Okay, now we have a membrane here, and we have a hole in the membrane. So that's interesting, right? You can kind of think as a mechanical engineer, when would I want a hole in my membrane? You might want to actuate that membrane. It comes down like this, right? And then fluid jumps through the hole. Or you can leave just a stiff membrane the way it is with a hole in it, and you made a nozzle, right? So you can do lots of cool things, and you can control the size down to micron levels. So you can make atomizers and things like that, where you can control droplet size exactly, which might be good if you use it in an engine, right? So if you want high efficiency burning of fuel, the smaller the droplet, the more efficient your fuel burning will be, and the more efficient your pistons will run. if you're doing a car application. Also rocket ships, all kinds of things like that that require tiny nozzles, and also for drug delivery systems. So, you know, there are a lot of engineers working on in medical devices. If you can make a drug delivery system that you can tune the droplet size to a very small range, then you can change the efficacy of the delivery of the drug. Different size particles will go to different parts of the lung when you breathe it in. So if you need the drug very deep in the lung, you make one size of particle. If you need it in the esophagus and the upper respiratory instead, you would make a different size set of particles for whatever drug you're trying to deliver, right? So, you know, that's really, really important. Or if you're making, you know, vape cigarettes, right? You might want to adjust the particle size and not use a heater to create the vapor, but actually use a mechanical system. And Dr. Jackson's kind of thinking about how to do that, because it's the heating of the material in the vape systems that cause a lot of the byproducts that end up going into your lungs and doing funny things. So if you can avoid the heating part of it and still create a vapor, an aerosol as it were, mechanically rather than through heat, you'll get a better product that way. Hopefully safer. Oops. So we saw that the crystal orientation may result in different etch rates. Some types of etch chemistry, for example, EDP at KOH, or wet isotropic etching of crystalline silicon. Then we doped the crystal with a bit of boron, and it too resulted in a change in the crystal etching properties. And then there's an example where you can use TMAH, which is tetramethyl ammonium hydroxide, and it can also etch 100. Okay. But that material will stop etching when you have 10 to the minus, let's see, 5 times 10 to the 18th per cubic centimeter of boron in it. Okay. So you might say, well, that's a lot of boron, but you know, that's 10 to the 18th out of 10 to the 22nd, right? So that's 1 boron atom every 10,000 silicon atoms will stop the etch, which is kind of amazing, right? So you don't need a lot of doping to create an etch stop. So when you think about it, it's only 1 boron atom per 10,000 silicon atoms. The mechanical properties of that membrane is the same as if it was pure silicon, but the chemical properties of that material are completely different when it's related to etching. And also it's different when you consider electrical properties as well. Okay, so a small amount of doping can radically change electrical properties and chemical etching properties, but it kind of leaves the mechanical properties alone. So that's something to keep in the back of your head if you ever work in this. Okay, so I'm going to stop here, and we're going to talk a little bit more about etching next time.